Okay, we're back. And we were talking about geometric pitch. We had a little bit of oops, but there really wasn't an oops. It was just fine. So I will explain. So R is not radius, as in the radius of the prop. It's the radius at the station I selected. So what station did I select? 30. And why did I select 30? Because it's 75% station. Now, I'll also tell you that I think your book has a different formula, and there is yet a different formula in the lab sheets. But I picked this one, I think, because I think it's actually quite easier. So it's 2 pi times 30 times the tangent of the blade angle. So I don't have my calculator, but I did it ahead of time, and I know that the tangent of 20, so tangent of 20 is 0.36397. And if anybody wants to check that, you can. So we have 2 pi times 30 times 0.364. So we'll just round that to 364. So 2 times pi is 6.28 times 30 times 0.364. And that would all equal 68.61 pitch inches. So what does that mean? That I got this 68.61. Woohoo, I'm done. Got a number. Does it mean something? It's the geometric pitch. And what does that mean?
For every revolution, it's going to move forward 68.61 inches.
There we go. For every revolution, it's going to move forward 68.61 inches. So what did we do? We ran out on the line and with a flash. Now it's late, so we had to use a flashlight, a tape measure, and a protractor. And we found somebody's propeller, and we measured the diameter. Yes, we divided it by 2. Then we measured from the hub out 75% of that, right? So we had what did we figure? We had an 80-inch prop divided by 2 was 40, multiplied times 0.75. We came up with the 75% station on one side. Took a protractor, figured out it was 20 blade angle was 20 degrees. And we ran in here and did the math. 2 times pi times 30, because that's the station, times the tangent of the blade angle. Came up with that. So it's 68.61 pitch inches. Now we could take it one step further if we wanted to. And we could do something like, okay, so what if the propeller was turning a certain RPM? We could take the pitch in inches, which I didn't really do ahead of time. We could say it's 2,000 revolutions per minute. And so we could figure out then for every minute how far it's going to go, and we can figure it out from there. And I actually did this exercise with my prop, trying to figure out what 1 degree of pitch would get me, and it was kind of interesting. So anyway, we could carry it all the way forward and do that. But so geometric pitch is, again, how far the aircraft will move forward in 1 revolution. Is that theoretical or absolute? So will it really do that?
No.
Nope. So what do we call what it really does? We call it effective pitch. So effective pitch is the actual distance. The plane moves forward. I'm going to put a line through this because I was just making a note. I don't want you to make a note and go, well, wait a minute, how come 68.61 equals 2,000 RPM? It doesn't. It was just an example. I could figure out if the plane was going 2,000 RPM, I could then extrapolate how far it would go, but I didn't do that. Yeah.
Is it important that we know how you get 20 inches to 0.36397, the tangent?
It's on your calculator,
Okay.
which I didn't bring mine in, but it's...
You put 20 and hit the tangent, turns that number?
Yep, and some of it's the other way around. Some calculators, it's 20 tangent, and some of it's tangent 20. So you just figure it out until you get 0.364, and then here you go. All right, the actual distance the plane, where was I? The actual distance the plane moves forward in 1 rev. All right. Effective pitch ranges from about 0% to about as much as 85% on most propellers. Why 0%? Give me an example of when it's 0%.
Not moving.
Not moving.
0% of the geometric pitch?
Effective. Yeah, I'm sorry, yes, 0% of the geometric. So here we have a geometric pitch up here of 68.61. What's my effective pitch if I have the brakes on and I'm not moving? 0. Then what is slip? Well, that's when you're coming in like this. Slip is the difference between the two. The difference between the geometric pitch and the effective pitch. So you can say geometric pitch minus effective pitch equals slip. I have a picture. I want to see it. That's in your book. If you open it up, you would see that. But I don't expect that. So here our airplane. This is where you want to be. This is where you end up. Difference is slip. Slip good or bad? That's bad. Don't want that.
How do you bring slip down?
How do you bring slip down?
Is that larger diameter?
Get a more efficient propeller.
So, larger diameter, more likely.
Would making it a larger diameter make it more efficient? Prince says yes. I say, I don't know. Probably. But at some point,
You can't do that.
you can't do that because, well, of two things. One, tip speed and clearance issues.
Yeah.
All right, so that brings me to, yes.
Is the slip also caused by the drag of the airplane?
It has nothing to do with that.
Well, but if you increase the drag of the airplane,
It's gonna get holding it back.
so,
Well, then the propeller won't turn fast.
well, okay, so to take your theory. So would the slip be the same? And it's like saying, would the propeller keep the same efficiency if I increase drag? So we're flying along in your plane. No, I have to use mine because I have two doors. And we open both doors up and push them out. By the way, that's why they don't have suicide doors on airplanes. And we increase a bunch of drag. Or what if we're dragging a banner? And would the prop be still the same efficiency?
Well, the prop would be, but is slippage the prop is still just as efficient, right?
No, because if slip increases, then efficiency has gone down.
It's not increasing your slip, though. It's increasing your speed.
Wait, what's that?
That wouldn't be the prop losing efficiency. I just feel like you're dragging a boat in.
I know. If you're dragging a boat anchor, you increase slip. And I would call that efficiency.
Because you would also change the angle of attack because you're spinning the RPMs higher, but
Yeah.
you're not going forward as much, so it changes the angle of attack, so thus more slip.
I would think so.
But that's different than, that's a function of it, it's not directly.
That's
If you're moving forward and you add a large, like a parachute or something,
Okay.
and you're going slower, you're working harder to obtain that same.
Hmm? That's what he's saying.
That's called
Slip.
slip.
That isn't what slip is,
It's the difference between effective pitch and geometric pitch.
but it isn't. It doesn't have anything to do with engine speed. It's for the same engine speed. Because there are too many other variables.
Geometrically, it should move X amount, but you only go Y.
Tell you what, I guess we could spend the next 20 minutes arguing about this, and there's how many Q&A questions on it?
One.
Well, not on that. So I don't want to shut off the dialogue on this, but at the same time, lots to go over. I would say that it does increase the slip, which to me, that is changing the effective pitch. And that is changing the Efficiency.
But you're changing power, RPM, because you're decreasing RPM because you have
Okay.
which is decreasing power.
Nope. You got the same RPM, same everything. He's got a ballistic chute but he packed it weird because he's a dragster guy. So he's got a dragster chute in the tail cone. So you're doing the exact same thing. Pops out a drogue chute. Will the plane slow down?
Yes.
Okay, so plane slows down,
Plane slows down, the propeller's working harder.
but he didn't change RPM.
No, it will change RPM. Because the propeller's working harder.
He's right about that. So he increases power, so there.
That doesn't increase power. You decrease RPM.
All right. I see your point. Can I move on?
Yes.
All right.
Did you get the answer?
He still doesn't know. Tyler's like, he already lost interest. So the moral of the story, honestly, I mean, the takeaway from this is don't put a dragster chute on the back of your airplane or drag boat anchors. You won't have this problem. Or open the doors, all right? So aerodynamic forces. Aerodynamic. All right, so we have the aerodynamic forces that we're going to talk about. And here we go, a picture of them. 5 of them. D and E are going to be very important to us in the next coming weeks. So another one of those, well, gosh, I hope we didn't bring that up again. Centrifugal force, which tends to rip the blades out of the hub and go spinning them off away from the plane. Torque bending force, which is going to twist the blades. Thrust bending force, which tends to pull the blades forward. Center of pressure, and centrifugal twisting force. These, and it's the reason why they've actually kind of changed. So if you look at A, B, and C, they're really representing a fixed pitch propeller. But when we get over here, it's kind of they change everything, even in the drawing, and that's a good thing. So what we're looking at actually is sort of a plane going straight up in the air. And so this is the spinner here. And so the center of pressure being off the center of rotation is going to want to make, it's like a wing. So it's going to want to drive this to, I wish they would have put this sideways, inline, which would be feather. Got that? And this one is going to make it go towards a low pitch. Follow? All right, we're going to cover that a lot more. No, I was hoping I'd actually change the orientation. Okay, aerodynamic forces. So first we have centrifugal. Centrifugal force. A force that tends to throw the blades, away from the hub. It causes stretching.
And the paint to fly off.
And the paint to fly off. That's why you got to paint those tips a bright color so the paint doesn't. It is the greatest force. It is the greatest force acting on the prop. However, this is a force that we can't use. We're going to use the other one. We're going to use, aerodynamic force to some extent. And to a greater extent, the centrifugal twisting force. So remember, there's centrifugal force and centrifugal twisting. So centrifugal twisting force is going to be we're going to use that later on to do stuff. Yeah.
Yeah.
This better not be a.
No, it's
No.
not an engineering. Do you measure?
Because I just had.
Blade migration on props,
Do I measure blade
or like in the field?
Yes, prop shop would. Especially if it causes stretching. This is something here. Let me see. Wait, 1, 2, greatest. Oh, may exceed. May exceed 7,500 times the weight of the blade. That is an impressive number to me. And it is for this reason that I'm very careful about what I do to propellers and why I don't stand in line with propellers, because that is a lot of force. Can I move that? What?
That's like when the belly is spinning.
Yeah, if it's stationary, it doesn't do that. That's why they droop down when they're It's when it's spinning. It's this one. When it is spinning, it wants to fly away from the hub. With how much force?
7,500 times the weight of the blade.
That's a little bit, isn't it? All right. Torque bending force. Let's say due to air resistance. Due to air resistance. Tends to bend the blades in a direction opposite of rotation. So what you can do if you have a twin that has a right and a left-hand rotating engine, if you swap them every annual, then the forces will even out.
That's a lie.
That's a total lie, because the props go the wrong way.
Paint them at the same time, Kevin?
and then you cut off the black and paint them, and it's all part of maintenance, man. Trust me. That's what we do in the field.
Is that a norm?
That's a norm. All right, thrust bending force. I cannot look at this picture without thinking of this. So thrust bending force. Now, while it is true that as the airplane is flying through the air, the blades will tend to move forward. And that home built by the time clock, the yellow one, has a black carbon fiber looking prop on it. It's called an Ivo prop. They're pretty cool. But I've actually stood in line with one, which I wouldn't anymore, and watched, I had a friend who had one, and watched what he did as he changed RPM. And you could watch this prop bend forward and back because it's very flexible. And so you can actually see this thrust bending force, which is kind of cool to watch it come back and forth and resonate. But the point I want to make is that even though the props do that, and this would be a metal prop doing that, nothing really freaks me out. Well, I shouldn't say that. What I hate to see is people tend to move aircraft by grabbing onto the propeller. And, well, it's wrong for a bunch of reasons. One, you guys now have built a propeller and you know that there's just a thrust flange in here and that you're pulling on that thrust flange, which it was made to be pulled on, so that's not such a huge deal. But it actually ruins the propeller. There have been, I've read reports, many reports, where especially on a hot day where propellers, they heat up, just even being in the sun, people have grabbed propellers to move the plane forward a little bit and not ruin the propeller, but pulled it out of alignment where it had to go off to a prop shop and get an overhaul just from pulling on it. So everybody does it. If you're going to insist on doing it, grab it right at the spinner. Don't grab it out at all. But on my own plane, you won't see me doing it because I don't want to ruin my prop.
Where do you move your airplane at? Push on the wing?
Well, if I have a helper, I'll say push on the wing strut. If not, I just use a tow bar and pull like heck.
Your plane's light.
It's light. Have you seen it? You're familiar with the C-130s out there, right? Mine's a C-150. Can you imagine how much bigger that is?
You see this big like that?
All right, thrust bending force. Let's see. Thrust loads. tend to bend the blade forward. That's why on the Skymasters you swap the front and the rear propellers. No, it's not true. Aerodynamic twisting force. Tends to twist the propeller towards a high blade angle. We're going to fix this slide. There we go. Okay, now we're facing the right direction here. All right, so aerodynamic twisting force. Now we got the plane of rotation going the right way. There's a thing called feathering a propeller, and it's the extreme. So we have one extreme is going to be a low pitch or low blade angle where this is going to be very flat, right, and in line. So if I were running it and it wasn't moving, if it's very flat and it comes around, I'm actually going to have a proper angle of attack coming at it. So that's very flat. And that's one extreme where this goes absolutely flat. The other extreme is feather, where this blade actually faces directly into the wind. And twins aircraft and a couple, very few, but some single engine aircraft will do this, but all twins will. So all twins, if you lose one engine on a twin, whether it's like the Skymaster that we had going today or like the 310 out there with the engines on the wings, engine on the wing is worse. So if you have an engine failure in a twin, you want to stop that engine from moving. Let's say you threw a rod or something. Well, that's just the prop is going to be windmilling, which is going to cause us damage. Not only is it windmilling, so when you're going through the air, the force of the wind is coming into the propeller. So it's robbing power out of the aircraft, if you will. It's going to make that side yaw back because it's having to windmill and drive a broken engine. Follow? So if I can stop that propeller from windmilling, so much the better. So feathering means to put the blade directly into the wind, so it's no longer an effective propeller. It's more like a little tiny wing sitting out there. So when it feathers, it goes right in the wind, and then the propeller stops moving. So all twins are going to have that. In fact, if you look at, I think somebody, when they ran the 310 last, they feathered the engine as they shut it down. So it's one side is actually feathered out already. So that's the extreme, is to feather it. So we have low pitch and then feather, which is the extreme high pitch. Okay. And so the point I want to make about that is that the two forces we have, the aerodynamic forces we have, first we have the aerodynamic twisting force, which is, it tends to drive the propeller towards the high blade angle, which is the feather position. All right. And that's, of course, because the center of pressure is behind the center of rotation. Center of lift pressure is forward the center of rotation, which is the midpoint of the chord line. And it's just aerodynamic forces. This one is different, all right? It's not an aerodynamic force, it's a centrifugal force. So, let me think. All right. If you had something on a string that was faced up and down like this, and I started to twist it on a rope and go round and round, it wouldn't stay this way. You can try, you can stand up and do it like this. Your arm's going to want to naturally go like this. Tim's going to do it. Tim's going to stand up and spin really fast, Tim. I'm just kidding. He'll get dizzy and fall down. So the propeller, just going on its own, is going to want to go to this very low pitch, right? So it's going around in a feather position. And the faster it spins, it's going to want to automatically rotate around. So we have the center of rotation, which makes it want to go like this, and centrifugal twisting force, which makes it want to go like that. Low pitch, high pitch feather. Got it? All right. Which one's going to win? Or will they be equal? Centrifugal's going to win all the time. So the center of, the aerodynamic twisting force, really doesn't come into play because it just only takes away a little tiny bit of the centrifugal twisting force. The centrifugal twisting force will always win. And I'll tell you where we're going to head with this is that if you have in a constant speed propeller, they're driven by oil pressure, which way they go. And if you had a twin engine aircraft and your engine failed and it took engine oil pressure to do something, would you want the blade to default into a feather position or default into a low pitch? You'd want it to go feather. So you're going to be looking for a twin engine aircraft, somehow have to reverse this effect, and they're going to put big counterweights on it. And so it's going to change the centrifugal twisting force from this to this by adding weights out on an arm. All right? But if you had a twin engine single engine aircraft, single engine, and you were having oil pressure problems or a governor problem or some problem that resulted in the prop not working, would you want in your single engine aircraft for your prop to go to feather, or would you want it to go to just a low pitch? You want to go to low pitch. So on a single engine, you're going to reverse this process, and you're going to let centrifugal twisting force win. And so if you lost all your oil pressure, well, to the prop, it'll say, because if you lose the engine, you're going to die. It's going to quit anyway. But it's going to automatically go to a low pitch. Should we fix this? It's like watching how sausage is made. Here we go. All right. Aerodynamic twisting force tends to twist the prop toward a high blade angle. And that's towards the feather position. And that's because center of lift is forward of the center of rotation. Don't really have that issue with a fixed pitch propeller. It's not going to move. The force is still there, but it doesn't necessarily move. And then we have the centrifugal twisting force. Which is different than the centrifugal force. Due to the mass of blade, force tends to move the blade toward a lower blade angle. Force tends to, I don't want to say that. Well, what the heck, it's shorter. Tends to flatten out the blade or lower blade angle. And this force is greater than aerodynamic. And we're going to use this one for, I'll write that, we'll use this force to move constant speed blades. And we'll talk about that when we get to that one. Nope. 5. Tip speed. Tip speed is the principal limiting factor for propeller efficiency. Oops, is a principal limiting factor for prop efficiency. What's the big deal about tip speed?
It has to be
Must
subsonic.
remain subsonic.
Must remain subsonic.
Must remain subsonic. What did you say, Hannah? Something like that? Okay. That is correct. So, and what happens? So, okay, big deal then. So what happens if we start going transonic into supersonic?
It'll
You
cause
experience
vibrations
a lot-
on the blade and it'll shatter it.
Well, you experience a lot more forces acting against the blade.
Yeah, have a lot more forces. So we start building up pressure waves. And what did you say, Dennis? Because that was good too.
It'll cause the blade basically to harmonize and shatter.
Yeah, can do that too. So it's some really bad things start happening. It's not just a loss of efficiency. You start actually destroying the blade.
And doesn't Bernoulli reverse once you go supersonic? So, right?
Yeah,
So instead of a lifting blade,
I hadn't really thought about it that way,
But
but
in transonic, it's different. It's a lot of forces acting against it.
yeah, I'm thinking more of the pressure waves that are set up in front of it, which then start blocking the actual air, which then you get the pressure waves built up, and then you start getting weird harmonics, and then
It'll be hard to get to supersonic.
be hard to get to supersonic.
It'll be hard to get to supersonic.
Because of the pressure waves built. Yeah. Just need more power.
But
But
back up just a little bit. Hold on. Yep.
all right, excessive speed. Causes flutter and vibration. I should find a video for flutter. If you guys have never seen a video of something fluttering in flight, it is phenomenally scary to watch. And what you see is
Do it.
you see a surface start to flutter and wave, and if it's not stopped immediately, then that part of the plane disintegrates and it just departs.
What was that one with the bridge?
The bridge one's a good one. Yeah.
You should bring it up.
I should bring it up. Yeah, test is on. You can just not pay attention. Test is on Friday if I get there or not. We're on page 9 of 22. You can do it at home. Okay. So let's see. Tips. Tip speed must be below. You know, I think most books say it must be below supersonic, but I really want to say it transonic.
Yeah, that's more accurate.
So, because that when you start,
The in between is
It's
just
the-
as rough.
yeah.
Not more.
in fact, that was what the whole thing with
The
the
X1.
X1. They up until then they were getting near the speed of sound and saying whoa, backing off, is where the X1 blasted through it, and it was like, well, hey, now it works. So this transonic is really a problem. And how do we keep the tips below transonic?
Limit RPM. Or
Okay, so limit RPM. How do we limit RPM?
gearing
Red
engine.
line.
Okay, geared engine. Geared engine, or what else can we do?
Limit red lines.
Mm, nah, well, obviously we could, but
Smaller diameter prop.
there you go, smaller diameter prop. So if I make the prop smaller diameter, what do I have to do?
Increase the pitch.
Increase your pitch. There you go. Okay. Let's see. Propeller load.
Why would you increase the centrifugal force? Like, I understand it's gonna take more of a bite, right?
Well, you're going to be losing losing the end of it.
Right. But wouldn't that change the angle of attack? Don't you want to keep it within the 2 to 4 degree range?
Well, because it's smaller, because it's shorter, you're not going to be getting as much of a bite as the bigger one. So you need to make up for that somehow.
Right. But then aren't you going to be out of your 2 to 4
Okay, so if you're
Less
at,
efficient.
out of your 2 to, you're right. So you start changing everything. So that's why blades are a certain length, That's why you're not supposed to just cut them. That's why the whole thing starts changing. We go right back to the first statement I made. You change one thing and the whole thing gets thrown out. So, prop load. Let's see. Do we have time for this? Yeah. Okay. The faster the prop turns, you guys okay down there?
We can see he's
I know, is he?
Yeah, I'm good.
Okay, good. All right. The faster the prop turns, the more power it absorbs. Or uses. We'll keep it kind of simple. It varies with the cube of the RPM. Double the RPM. I'll put that's kind of cool. Double the RPM. Equals 8 times the power required. Or power absorbed. Which, I don't know. As Phil would say, it's a little bit of a gee whiz fact right there. 80% of horsepower is used for thrust, and 20% for friction and slip. Kind of stinks, doesn't it?
So probably a good paint job on your prop makes a difference.
Especially after someone gets split off the end.
I know.
Flop around there.
It's all flapping on the end. Speaking of prop paint jobs, do you know what the FAA is kind of on the hunt for right now? Are polished propellers.
Oh, corrosion.
No, there's no data to polish a propeller. There are only a select and rare instances on some radial engine propellers where the manual actually says that you can polish them. All other propellers in the manual say and paint.
That including the cone?
Huh?
Was that including the cone or not?
The coat?
Cone.
The cone. Spinner?
Yeah.
No. No, it does not. Because that's part of an airframe thing.
Polishing them instead of painting them?
Uh-huh. Looks pretty, but not supposed to. All right, we have prop load efficiency. We already talked about that. I think we've talked about brake horsepower in another class. Asymmetric loading, also known as what? P factor. Ah, somebody was awake. All right. What is P factor? Come on. All right. So as I pull back on the stick and I start to climb, one side of the blade is going to get a larger bite than the other side. Which side? So we'll all be on the same one. Is the engine going to go to the right or to the left? To the right. Okay, so it's going this way, go up. So it's this side is going to get more of a bite. So the descending, which is going to make you want to go that way, which is which way? All right, so that's P factor. Since you guys already know about that.
Unless you fly World War II or coming from England.
Yes, I was going to talk about that. What about gyroscopic precession? Can I get that from a propeller?
Yes.
All right. Did I tell you my story about the poor guy who was an RAF pilot?
Yeah.
Okay. So the poor guy was an RAF pilot, fought in the war. Hero in my book. Used to an airplane that is going on takeoff, so on a tail-wheeled aircraft, as you're kind of taxiing down and you go to take and you bring the tail up, you're moving the disc on the front from a plane that's this way to this way. So gyroscopic precession, if it's going around this way, and I bring the tail up, it's like pushing on the top of the prop, right? Which has an effect where? So now it's like I went out to the tip of the prop and pushed on it. So which way is the airplane going to go? Left. So if you're flying a tail-wheeled airplane, you have to instantly apply right rudder, or you're going off that way pretty hard. But this poor guy is used to an engine that didn't go this way; it went that way. So which way is he used to going? He's used to going to the right. So he thought about that. Is he used to go on the right? Yes. So we have to add which pedal?
Left.
Left. But he's in an airplane that's already going to go left. So the tail comes up, he puts on the left pedal, and he went
Way left.
way left, off into the mud, and flipped the airplane over.
Props right.
It was, yeah. And it was a fabric airplane, so we had to do a lot of work. All right, let's see. So, well, I'll just put these little notes in here. The things that we... So 7 was efficiency, which we already talked about. Thrust horsepower, actual amount of horsepower that an engine propeller transforms into thrust. Thrust is perpendicular to the plane of rotation. We have brake horsepower, actual horsepower delivered to the prop. And we talked about asymmetric loading. Or P factor. And that brings me to propeller clearances. According to FAR 23.925, last I looked, we have minimum clearances that must be set for aircraft. And I'll give you some notes on this. So if we have a tail-wheeled aircraft, you must have 9 inches. Actually, let's do it this way. Prop clearance is necessary. Let me see. We got to prevent prop damage and reduce aerodynamic interference. So tricycle gear. Where's my tricycle? Here's my trike over here. So tricycle, minimum of 7 inches between tip and the ground. 7 inches between tip and the ground. But when? There's struts here and all kinds of stuff. The answer is at taxi takeoff position with gear statically deflected. FA words. Static deflection is simply the amount that they spring compression under the weight of the aircraft. So that would, another way of say that is 7 inches under normal deflection. I don't want to say with strut deflated, because they also say, well, what happens if the strut is deflated and the tire is blown? Then it's just a positive clearance. So under normal deflection, 7 inches. With the strut failed, tire blown out, as long as it didn't hit the ground, you're fine. Tailwheel aircraft, maximum of 9 inches at the taxi/takeoff position with gear deflected, whichever is least. So in this case, least would be with the tail up. You want 9 inches right there. And normal deflection. Seaplane, 18 inches between the water and the tip. I'm assuming with calm water. And structural clearances. We must have 1 inch radially between the tips and the structure. Like here, tips between the fuselage and here. 1 inch. Isn't that crazy? That's like, yeah, I don't know about that. Hey, not my rules, but that is really close. Half an inch longitudinally between blades or cuffs and stationary parts of the airplane. So that's going to be inside of here. So ½ inch in there. Positive clearance between other rotating parts, the prop, spinner, stationary parts of the plane. In other words, positive clearance between cowling and spinner. So cowling and spinner is right in there. And what do I got? ½ inch here between the other parts. That's what it was. And so you want some notes on that? Or did you write it all down? You wrote it down? No. Prop clearances. All right. You're like, no, I was just enjoying the ride right there. All right, prop clearances. What do we say? proper clearance is necessary. Proper prop clearance. One, to prevent prop damage. Hey, care to guess how much a new constant speed propeller is going to run?
20 grand.
30 grand.
30 and up.
30.
That's it?
1,000. I make that a year. And reduce. That's a constant speed. Reduce aerodynamic interference. All right, tricycle gear. Minimum of 7 inches between tip of prop and ground. That is with gear statically deflected.
Statically deflected means what exactly?
All right, statically, S-T-A-T-I-C-A-L-L, statically deflected is the amount that a spring compresses under the weight of the equipment. So I would say that that would just be normal deflection. Load up, and when you have the strut set properly and you properly load it, normal. So, and this is only, this kind of helps, only quote, positive clearance is required with the strut deflated and critical tire blown. Flat is probably a better word. Flat. Not blown up, but flat. What's critical tire mean?
The nose gear.
It means the one that's going to make it bad. Whatever makes it the worst. Tail wheel. If I would have used the term conventional gear, would that be a tricycle geared airplane or tail wheeled? Which one's conventional? Tail wheel's conventional. Which one's better?
Depends on your opinion.
Minimum of 9 inches. And that is at taxi or takeoff position with gear deflected. Whichever is worse. And because the taxi and the takeoff position for a tail-wheeled airplane are two different things. Taxi position is with the tail down. And even though you can take off in that position, normally you bring the tail up, which brings the prop closer. So if you were designing an aircraft or wanted to check it, you would actually have to put the prop on, put it facing down, lift the tail wheel up and level the aircraft and then measure it. Seaplane. Anybody remember what that is? 18 inches, right? Tip to water. And structural. This is from the prop to the other things. So 1 inch radially. That'd be like tips to fuselage on a twin. Or 1/2 inch between blade or cuff. Blade, sometimes you can put, you don't see it very often, but cuffs, they actually are like a fairing piece that bolts on around the hub, near the hub of the prop. So blade or cuff, which would be near the hub. And stationary parts. Of the airplane. And the drawing that they were given right here was a 1/2 inch between that nose wheel and the prop. I have never seen an aircraft built with a 1/2 inch clearance. It's usually a little more. And positive clearance. Between other rotating parts. Such as between the spinner and the cowling, things like that.
These clearances differ if you had 4 engines, like the C-130, for example?
It doesn't say anything about adding engines. It is just there. Those are the clearances. But a C-130 is probably not, I don't know if it's built to FAR standards. But at the same time, I doubt they have it shorter than that. All right, so tomorrow we can pick up with number 10, types of propeller configurations.